Welcome to Binary Bytes and Bitwise Operators in Python. My name is Chris, and I will be your guide. This course introduces you to binary number concepts and how you can use them in the Python programming language. In particular, you'll learn about binary numbers, bitwise math and truth tables, number representations, fixed and arbitrary precision integers in Python, bitwise operators in Python, frequent use of binary and bitwise operations, big endian and little endian byte orders, and overloading bitwise operators. A quick note about versions. The code in this course was tested using Python 3.9. Nothing is very version specific, but f-strings are used in some places. F-strings were introduced in Python 3.6, so to follow the code along exactly, you'll need at least Python 3.6. Everything is digital these days. At the time of this recording, I'm shopping for a new washing machine. It is pretty much impossible to find one with a mechanical control anymore. The retailers keep telling me how great it is that it can talk to my phone via Bluetooth. Until my phone figures out how to do my laundry, I'm not sure why this is important, but it does underline the fact that computer processors are everywhere. CPUs in computers are built on transistors, which are tiny components that act like switches. Every piece of data in your computer is represented through a series of these switches with the patterns of on and off forming a binary number. The ones and zeros in the binary number correspond to the on and off states of these switches. These binary numbers are then mapped to represent your data, such as going through a numeric transform to translate binary to decimal, doing a code lookup to translate binary to a character, or directly influencing the state of hardware in your system. Python isn't the easiest choice for manipulating raw binary data. It has lots of tools that can help you out, but some of the high-level language features that make it easier to code other things can make dealing with binary a bit more of a challenge. In grade school, you learned simple math operations like addition and multiplication. With binary data, you can do these operations as well as some others. There is a family of binary operators that are called bitwise operations. Each of these operations either combines two binary values into a third or manipulates the bits in a binary value. Most of the operations can be thought of as a series of steps performed on the bits within the binary number. The first bitwise operator I'm going to talk about is AND. AND combines two binary numbers, comparing the corresponding bits in each. If the corresponding bits are both 1 in the numbers being combined, then the bit is 1 in the result. OR also combines two binary numbers. This time, the bits in the resulting number are 1 if the corresponding bits are 1 in either of the operands. XOR is short for exclusive OR. It is like OR, but the bits are on only if the bit is on in exactly one of the operands. If both operands have a bit value of 1, the result will have a value of 0. Everything up until here has combined two operands. The next three operate on a single value. Not, also known as negation or inversion, flips the state of all the bits in the number. All the ones become 0 and vice versa. This is the left shift. All the bits in the result are the operand's value shifted to the left by n positions. The new bits pushed in on the right-hand side have a value of 0. Corresponding to the left shift is a right shift, moving the bits to the right instead of the left. Using bitwise operators, you can create and manipulate flags, access a portion of a number, or manipulate raw binary data. Next up, I'll dive into binary numbers. The zeros aren't so bad, but if you land on a 1, it's a bit pointy. Thanks. Tip your waitress. I'll be here all week. In the previous lesson, I gave an overview of the course. In this lesson, I'll be covering binary numbers. Computers are, well, everywhere. At the heart of all the digital goodness in our lives is one or more microprocessors. Inside a microprocessor, there are millions to billions of transistors. The funky collection of lines on the right is the circuit diagram symbol for a transistor. When an electrical charge is applied to the transistor's base, current can flow through the transistor between the collector and the emitter. Turn the charge off, and the current stops flowing. Transistors are small switches. Apply a charge, and the switch is on. Remove the charge, and the switch is off. By changing the charge to different values on a series of switches, you can form a pattern. Switches that are on represent 1, switches that are off represent 0. These patterns can be used to represent other things. The pattern 101 means the number 5. This particular mapping is based on a mathematical transform. I'll explain more about that later. The patterns can mean other things as well. Pi gets approximated by a 16-digit floating point number, which is represented by the following binary code. This code is actually comprised of 3 numbers, a sign indicator, and an exponent value, and a fractional decimal value. The letter A is ASCII 97 in decimal, which in the CPU is represented by this binary value. Even Mona Lisa's sly smile on your screen is really just a large array of these numbers. Each pixel in the picture is represented by a number. This drab-looking square of greenish is the hexadecimal number 7F8053. The hex number breaks down into 3 parts: the red, green, and blue that make up the color. 7F8053 is decimal 8,355,923, or this long string of binary digits. It's binary all the way down. So what is this binary number stuff? Let's take a quick detour and think about the numbers you probably know a little better. Decimal. Consider 4,239. This number can be broken down into 4 parts. 4,000 plus 200 plus 30 plus 9. Each of these numbers can be thought of as the combination of a number and a power of 10, with 1,000 being 10 to the 3, 100 being 10 squared, 10 being, 10, and the ones digit being 10 to the 0. Although base 10 feels right or special to us, that's just because it is what was taught to us at a young age. There's an argument that base 10 really only exists because of the number of fingers we have. Historical civilizations have used different bases. The Babylonians used base 60, while the Mayans employed 2 different bases, base 20 and base 360, depending on whether you were a priest or not. Those might seem kind of crazy, but they actually make math with numbers like 12 easier. How many hours on a clock? How many degrees in a circle? Yep, you're using more than just base 10 yourself. You're just not necessarily conscious of it. A number can have any integer base. Commonly in mathematics, the subscript here indicates the base. 4,239 base 10 is subscript 10. 4,239 base n has subscript n. For the general case of base n, each digit is a power of n. 4,239 base n is 4 times n cubed plus 2 times n squared plus 3 times n plus 9 times n to the 0. Note that no digit in a base n number can be larger than n itself. In base 10, each digit must be less than 10. Back to those switches, that on and off stuff, binary numbers, or base 2. Just like base 10 or base n, each digit is a power, in this case of 2. The number 1011 in binary is 1 times 2 cubed plus 0 times 2 squared, still 0, plus 1 times 2, plus 1 times 2 to the 0. This gives you 8 plus 2 plus 1 in base 10, for a total of 11 in base 10. In computer science, there are 4 bases that are commonly used. Decimal, because that's what humans are used to. Binary, because that's what the machines want. And the last 2 are things that translate back and forth to binary easily. Octal, which is base 8, and hex or hexadecimal, which is base 16. Both octal and hex map to binary values, and with a bit of practice, you can convert them in your head. 5 in decimal is 4 plus 1, giving 0101 in binary. 2 squared plus 1. Octal, or base 8, allows for digits to be up to and including 7, so decimal 5 is also 5 octal. Hex, or base 16, allows for digits up to 15 in decimal, so one more time, the answer is also 5. Let's try another one. 8 in decimal is 2 cubed, so the fourth bit is on. 8 decimal is bigger than the maximum value of a digit of 7 in octal. So just like the other bases, you add a digit and roll the counter over. Or, going the math route, 10 octal is 1 times 8 to the first power plus 0. In hex land, you're still under 15. So far, the conversion from decimal to hex is pretty simple. It will get worse, I promise. Let's add one more to our 8 and get 9. I didn't even have to use my fingers. Adding 1 in decimal means adding one more in binary as well, so the first bit position increments. Adding one more to the octal value, so the digit goes up by 1. And good old hex still isn't complicated. It's coming, wait for it. This time I'll add 2 more to the decimal value, and that means incrementing the binary value by 2. That's a power of 2, so in this case, just turn on the second position. 2 more to the octal case still hasn't exceeded the max digit, so 1 octal becomes 13 octal. Notice that I don't call these 11 and 13. 11 and 13 are decimal concepts. For clarity, I will try to remember to keep using the digit style. This is the technically correct style, but most people won't want to be corrected if they use the incorrect style. You will hear people say things like 13 octal. All right, hexadecimal is base 16. That means the largest digit can be the equivalent of 15. How do you represent 15 as a single digit? You switch to the alphabet. 10 decimal is A in hex. 11 decimal is B in hex. That goes all the way up to 15, which is F. Last one, let's do something a bit bigger. This time I'm going to start on the right-hand side with the hex value. B5. Remember that B is 11 decimal, so this is 11 times 16, because this is base 16, plus 5. This turns into 265 in octal, and 10110101 in binary. I've grouped the binary number into 2 sets of 4 digits. This is done on purpose. Each of these 4 digits directly corresponds to a digit in hex. This is why hex gets used. It is a convenient short form for binary. 1011 is decimal 11 or B in hex, and 0101 is 5 in both decimal and hex. If you have the binary equivalents of the 16 digits of hex memorized, you can quickly substitute one value for another. Fun fact, and this is the problem with my sense of humor, you're never going to believe what I'm about to say is true. Half a byte, that's 4 bits, or a single hex digit, is called a nibble. Who says computer people can't be fun at parties? And of course, in the more human readable format, 11 decimal times 16 plus 5 is 181 decimal. Now that you've got binary in your brain, next up, I'll show you bitwise operations that affect binary values. In the previous lesson, I showed you the ons and offs of binary numbers. In this lesson, I'll be talking about operations on binary values. Bitwise operations affect one or more bits in a binary value. The most common bitwise operations are AND, OR, XOR, NOT, and shifts. Bitwise AND, noted as a single ampersand in most programming languages, combines 2 binary values into a result. Each bit in the values being combined is compared. If they're both 0, the resulting value is 0. If either of them is 1, then the resulting value is still 0. And if they're both 1, the result is 1. Bitwise operations can be expressed using something called a truth table. The header row and header column contain the values of bits being compared, and their intersection in the table shows the result. So, 0, 0 in the blue meet to form 0 in the gray. 1, 1 in the blue meet to form 1 in the gray, and the mixed values in between. Consider the following example: 1, 0, 0, 1, 1, 1, 0, 0, ANDed with 0, 0, 1, 1, 0, 1, 0, 0. Line up the ones, and any position with a 1 in both values results in a 1. Everything else results in a 0. Bitwise OR, noted as a single pipe symbol in most programming languages, combines two binary values. Each bit is compared, and if either of them is on, the resulting value has the corresponding bit on. 0 or 0 is 0, 1 or 0 is 1, 0 or 1 is 1, and 1 or 1 is also 1. Here's the corresponding truth table. And using the same numbers from before, anywhere there is a 1 in either number results in a 1 in the outcome. Bitwise XOR, also known as exclusive OR, is usually a caret in most programming languages. Exclusive OR is like bitwise OR, except both values being 1 results in 0. Only one of the bits can be on exclusively. 0 XOR 0 is 0. 1 XOR 0 is 1. 0 XOR 1 is 1. And the exclusive part, 1 XOR 1, is 0. Here's the corresponding truth table and an example. Follow the ones, but only if they cross a 0. There's the result. Up until now, all the bitwise operations you've seen have operated on two values. The NOT is different. It is a unary operation. Bitwise NOT is usually the tilde symbol in most programming languages and is responsible for inverting each bit in a binary number. So 0 becomes 1, and 1 becomes 0. Going through an example, everything flips to the other case. There are two bitwise shift operators, one for shifting left and one for shifting right. These are usually denoted as double less than and double greater than in most programming languages. Each shift operation includes a parameter, a number that indicates how many positions the bits are going to shift. The following examples are a bit messy, as they combine both binary and decimal numbers. Note the subscript next to each number. Subscript 2 means binary, or base 2, while subscript 10 means decimal, or base 10. 1 shifted left by 1 position gives 1, 0 binary, decimal 2. 1 shifted by 2 positions gives 1, 0, 0 binary, or decimal 4. Note that the new digits shifted into the lowest positions are all zeros. 1, 0, 0 shifted right by 1 position gives 1, 0. The rightmost digit of the original is chopped off. 1, 0, 0 shifted right by 2 positions gives 1. Because each digit in binary represents a power of 2, shifting left and right are the equivalent of multiplying and dividing by 2. This is like multiplying and dividing by 10 in decimal. Just add or remove a digit. 0 shifted left is still 0, and likewise 0 shifted right is also still 0. Here's a trusty example. With a left shift, digits move left and zeros come in on the right-hand side. And now here's the right shift. The rightmost digits get chopped off. So far, everything I've been talking about is theory. As is often the case, practice is a bit messier than theory. Computers use binary values to represent numbers. The problem is, computers have limited space to store things, and that limitation has an effect on bitwise math. Consider an 8-digit binary number being stored in a place with enough space for 8 digits. What happens when you shift this left? Well, you can't put a 9-digit number in an 8-digit space. Complications ensue. This means bitwise manipulation of binary values may not have the effect you may think it does, depending on the programming language and the data type within the language that you're using. In theory land, everything so far has been an unsigned number, that means everything is zero or more, and all operations were logical. That means the bits are played with no consideration for what they are representing. These two assumptions are handled differently in different programming languages. Some languages even have the behavior change based on the data type being used. Did you notice the slide's title? If you're not familiar with the phrase, it's Latin for buyer beware. As a purveyor of the Python programming paradigm, you may find everything isn't peachy. Those two assumptions I just stated about Theoryland, neither of them apply to the practice of Python. Python's integer isn't unsigned, it can store negative values. The way the negative values are stored impacts the second assumption about bitwise logical operations as well. Next up, I'll show you how that last sentence I just uttered will make your life complicated. In the previous lesson, you learned about bitwise operations. In this lesson, you'll learn all about the different ways binary is used to represent numbers and why that makes bitwise operations have weird results. Binary, outside of the computing world, is a series of powers of 2 which on its own can only represent numbers 0 or greater. Computers use binary to represent numbers, but they store those values in a finite space in memory. A group of 8 bits is called a byte. A single unsigned byte can hold from 0 to 255 decimal, or 0 to 11111111 in binary. To store numbers larger than 255, you need multiple bytes. The C programming language has 4 different ways of storing integers: char, short, int, and long. Each of these is comprised of a different number of bytes. And what, you might say, about negative numbers? Such an intelligent question. You have to store those differently. C has 2 variations on those 4 types I just mentioned: signed and unsigned. An unsigned char is a single byte ranging from 0 to 255. A signed char is also a single byte, but in decimal ranges from -128 to 127. The same 256 spots are used, but they're mapped to different numbers. One of the complications of limited storage space is what to do when an operation causes a value to exceed the maximum for that storage space. This is referred to as an overflow. Consider a 1 byte binary number containing decimal 10. Adding 1 just flips the rightmost bit. Well, what about a 1 byte binary number with all the bits set to 1? What happens when you add to it? Overflow. The number resets to 0. There is usually a signal to the programmer that such an overflow happened, but not always. Let's talk about negative numbers. A lot. The next 7 slides are all about negative numbers. What might seem simple on the surface decidedly is not. Sign magnitude is one strategy for representing a negative number. It uses the leftmost or most significant bit to indicate whether a number is positive or negative. If the leftmost bit is 1, the number is negative. Positive numbers for a single byte sign magnitude integer range from 0 to 01111111 in binary. The leftmost bit has to be 0 for the number to be positive. That gives you 0 to 127 in decimal. Negative numbers are the same, but with the leftmost bit set to 1. Well, that's a little odd. 1 and all zeros is 0, but with the sign bit set. This is called ambiguous 0. There are 2 different ways of representing 0 in sign magnitude representation. 2 zeros isn't the only problem. Addition is also problematic. You can't just add the bits together. Consider the following example. 0 plus 0 is 0. 1 plus 1 is 1 0, carrying the 1. Passing through the carry gives you 1. Then 1 plus 1, carrying again. 1 plus 1, carrying again. And finally 1. The end result of adding 42 and negative 42 this way is negative 84. Let me just get a calculator quickly. Yeah, nope, that's not right. You can't just add two sign magnitude numbers and get the right answer. An early solution to the problems with sign magnitude representation was 1's complement. The leftmost bit still indicates the sign, but the negative value is stored as its complement, i.e., all its bits are flipped. This weird little trick actually solves the addition problem. Positive values are the same as sign magnitude, only the negative values are different. 1's complement, like sign magnitude, still has an ambiguous zero. You can't have everything. Let's look at some examples to make this a little more clear. The single byte 1's complement value for 0 is 8 zeros. The complement of that is an ambiguous 0. It flips the sign bit and complements or inverts all the other bits. This is the two representations for 0 in 1's complement. Here's positive 1. Negative 1 is the invert of positive 1. Here's 2. Negative 2 is the invert of positive 2. And the same goes for all the way up to plus or minus 127. What's better than one complement? Well, two complements, of course. This is the most common mechanism for storing negative numbers in modern machines. It removes the ambiguous zero problem and makes a couple of the corner cases in addition easier. The leftmost bit is still used for the sign. Negative numbers are still a complement, but this time they're the complement plus 1. This is called an asymmetrical representation. There are more negative values than positive ones. For an 8-bit byte, the range is minus 128 to positive 127. You can think of the most significant bit indicating both the sign and a magnitude. You can see it here in the chart. Bit 7 is a negative magnitude. Let's try some 2's complement numbers. 0 is not ambiguous. There's only one representation. No negative 0 in this case. Positive 1, let's complement it and then add 1. That gives you the all ones to represent the negative equivalent. Positive 2, complement it and add 1, and that's plus or minus 2. At the upper end, the biggest positive number is 127, which, when you look at the complement, shows you've still got one more bit that you can turn off. So minus 128 is 1 and all zeros. Consider these three different representations and what it would mean to perform bitwise operations on them. Most of the time you're doing bitwise operations, you really don't care about the negative representation. You're tracking bits, turning them on and off. Being explicit about this and using an unsigned integer is your best bet. Performing a bitwise operation on a signed value may result in the signed bit changing, and depending on the kind of number representation, the same operation will impact the value differently. In the following table, I'm going to show you the three types of a negative number representation. For each case, I'll show a value, the value knotted, and the resulting decimal numbers in the three representations. 0, 1, 1, 0, knotted, is 1, 1, 1, 1, 1, 0, 0, 1. The decimal value in sign magnitude is 6, and the knotted value is minus 121. The same two values in 1's complement give 6 and minus 6, and 6 and minus 7 in 2's complement. The same two binary values give 4 different variations on what they mean. Let's try it again, this time with 1001, 1101. Here's the knotted value, minus 29 sign magnitude, 98 for the knotted value, minus 98 for 1's complement, minus 99 for 2's complement, and 98 pops up again for the knotted value. How about one of the edge cases? Here's all zeros. Here's the invert, 0 in sign magnitude, and the knotted value is minus 127. 0, ambiguous 0, 0, and negative 1. And because I'm having so much fun, one more. Literally one more. Here's the knotted value. That's 1, minus 126, 1, minus 1, 1, and finally, minus 2. Have I convinced you that you should be using unsigned integers yet? Everything so far has mapped to powers of 2 somewhat directly. That doesn't have to be the case. Floating point and fixed point representations are different altogether. You don't typically do bitwise math on these types of numbers, so if the details of how these are stored doesn't interest you, I'll see you at the next lesson. Floating point numbers are based on the IEEE standard 754. These are a lossy representation of non-integer numbers. They're lossy because they aren't precise. As you saw in the second lesson, you can store 16 digits of pi, but that's it. Good enough for most cases, but it's still not technically pi. A floating point number is composed of 3 parts: a sign bit, an exponent, and a mantissa. This is similar to scientific notation. The name floating point comes from the fact that the number of digits to the right of the decimal isn't fixed. The decimal point floats around. The standard defines several variations. The two most common precisions are single float, which is stored as 32 bits or 4 bytes, with a sign bit, 8 bits for the exponent, and 23 bits for the mantissa, and a double float, which is stored as 64 bits or 8 bytes, still with a single sign bit, 11 bits for the exponent, and a whopping 52 for the mantissa. Let's look a little deeper at the single precision floating point number. The sign bit is 0 for positive and 1 for negative. That should seem a little familiar. The exponent is 8 bits. The number is treated as an unsigned value. To get small fractional numbers, you need a negative power. That's done by biasing the exponent. That means the raw number actually represents 127 more than the actual number. Subtract the bias and you get the right value. The mantissa is 23 bits. This part represents a fraction, where each bit is a negative power of 2. For all exponent values except 0, the fractional portion assumes a 24th bit to the left that has a value of 1. That gives you 24 bits of precision packed into 23 bits of space. And it means you have to add 1 to the raw mantissa to get the number it actually represents. Let's look at an example to clear up this messiness. All that stuff on the previous slide breaks down into this formula. The value the binary digits represent is minus 1 to the power of the sign bit times 2 to the power of the biased exponent times the mantissa plus 1. Consider this long mess: 0 for the sign, 128 for the raw exponent, and a whole bunch of digits for the raw mantissa. The mantissa breaks down into the following powers of 2, with the position of each on bit corresponding to a fractional power of 2. Turning those into actual fractions, and you get about 0.57. Plugging all that into the original formula, and look at that, pi. If you remember the pi from lesson 2, this one has less precision. The pi in lesson 2 was a double float. This one, being a single, means there are fewer significant digits to the right of the decimal point. Floating point numbers are only approximations. Some of them cannot be precisely described. You can see this easily in practice with the handy REPL. I might have to dig out my calculator again, but I'm pretty sure that's not right. These sorts of errors are very bad for money. Fractions of a cent can add up over time. Don't believe me? Go watch Superman 3. Richard Pryor wouldn't lie to you, would he? The answer to this problem is fixed point math. A simple version of this is all numbers are made up of 2 parts, the part to the left of the decimal and the part to the right. As long as you don't overflow either of those two parts, you're good. Although fixed point doesn't have the approximation problem that floating point does, it also doesn't have a dedicated part of the CPU that specializes in doing math with them. This tends to make fixed point more expensive computationally. The short version of that is fixed point is good for money calcs, but slower. Python has a fixed point library called decimal. It allows you to set an arbitrary precision to the right of the decimal point. Want even more precision for your numbers? Python has the fractions module that represents the numerator and denominator of a fraction separately. It supports doing operations on these objects, finding the lowest common denominator of the result. You can get the floating point equivalent if you like, delaying the creation of the imprecise thing to the last step in your calculation. Want some actual Python in your Python course? You've been patient. Next up, I'll talk about how Python stores integers to prepare you for the effects of bitwise operations in the lesson after. In the previous lesson, I showed you all the different ways to be negative, numerically, that is. In this lesson, I'll run down how Python stores integers so that in the next lesson you can be prepared for manipulating their bits. Python has two different ways of storing integers and seamlessly switches between them. The first is fixed precision. This is based on the underlying C language's signed long. That's an 8-byte integer on most platforms. And the second is called arbitrary precision, which allows you to store numbers past the maximum specified by 8 bytes. In fact, arbitrary precision has no maximum value at all. On a 64-bit platform, the 8-byte representation of an integer can store from -2 to the 63 all the way up to 1 less than +2 to the 63. That's an upper limit of this very big number. To store negative values, Python's fixed precision integer uses 2's complement storage. As you may recall from previous lessons, flipping bits on a 2's complement number can have strange effects. Then what if a 19-digit number is too small for you? Well, Python's got your back. The arbitrary precision integer has no limit and is based on a series of numbers stored in base 2 to the 30. Yep, you read that right. Not base 30, base 2 to the 30. I'm sure the Mayans and their paltry base 360 are jealous. As an example, this uncomfortably large number is stored as 973 plus 4,353 times 2 to the 30 plus 50,934 times 2 to the 60. Python conveniently switches back and forth between fixed and arbitrary precision based on the size of the number being stored. In fact, Python does something even trickier than that. Everything in Python is an object, integers included, so there's more overhead in storing them than just the 8 bytes. Common integers are cached at startup and treated as singletons. If you're bored someday and want to see some internal magic, use the id function to look at integer values between -5 and 256. The id function shows you the unique identifier of an object. New instances of the same number result in the same ID. With values between 5 and 256, new instances of the same number result in the same ID. Do that with a number bigger than 256, and you'll get multiple instances, no singleton. The compiler will even do further optimizations if the same number shows up in the same line. Lots of things baked in here to help you get some performance with the common numeric cases. Arbitrary precision numbers are sometimes referred to as big nums. Doing math on big nums is expensive. Unlike a fixed precision integer or a float, the CPU isn't built to do this specifically. Of course, if you're playing with numbers this big, the precision you get out of a big num might be worth the performance trade-off. What about negative numbers? Well, arbitrary precision numbers don't use 2's complement storage for negatives. I'll get back to that in just a second. Doing bitwise operations on arbitrary precision numbers is a multi-step process, with even more steps if the value happens to be negative. First, it has to be converted to a series of bits in 2's complement form. Then, the bitwise operator is applied. Then the result is converted back into an arbitrary precision integer. This back and forth ensures that bitwise operations do the same thing regardless of the size of the integer. Consistency is good, but of course, that is consistency with 2's complement, which I believe I have mentioned is a bit weird with bitwise operations. Just a quick recap before getting into the actual bitwise ops. Python doesn't have an unsigned integer. It uses 2's complement representation for negative numbers, which can have surprising effects when interacting with bitwise operations. But for most use cases, this doesn't really matter. Typically, if you're doing bitwise math, you're doing it on positive numbers that are small enough to be using the fixed precision representation. Now that you've got a handle on how integers are stored in Python, let's do some bitwise ops. In the previous lesson, I introduced you to the two ways Python stores integers. In this lesson, I'll show you the and, or, and not bitwise operators in Python. This course has a lot of theory in it, and in case you skipped straight to the Python stuff, here is a quick recap. Binary storage is founded on base 2 math, with each bit in a binary value representing a power of 2. Negative numbers can be stored in several different ways, the most common of which is called 2's complement representation. Python has two internal mechanisms for storing integers, which it switches back and forth between: fixed precision, which is typically an 8-byte number, and arbitrary precision, which is a big num object representation without an upper limit. One complication for bitwise operations is that Python does not have a native unsigned integer data type. Okay, good enough. Let's open up the REPL and do some bitwise math. I'll start out with a lowly small integer. When I type it in, the REPL shows the decimal representation. Python supports the specification of an integer in a number of formats. The 0 prefix specifies octal. 52 in octal is 42 in decimal. Note that some other programming languages use a different prefix for octal, just a leading 0. Python explicitly disallows this to avoid confusion. The 0x prefix specifies a hexadecimal number. 2a in hex is 42 decimal as well. Want to take a guess at the next one? Yep, 0b is the prefix for binary, yet another way of getting 42. Note that these different input methods are not generating different kinds of numbers. They're just different ways of inputting the same 42, stored the same way internally every time. Let's put this in a variable. No surprises so far. Now, what if you want to see the binary representation of this value? There are several ways of accomplishing this. If you're okay with a string representation, you can use the formatting feature of the f string. Here, the $b says to output the number in binary format. This is often one of the easiest ways of debugging a number that you need to see in binary format. You can further adjust the format specifier to indicate how many digits. This f string shows an 8-bit byte. There are also a series of functions that you can use to convert to the string versions of different number representations. Oct returns the octal format. Hex returns the hexadecimal format. And bin for the binary. Let me finally follow through on my promise and do some bit math. Here, I've combined two binary values. Recall that AND looks for bits that are in both numbers. In this case, that's the third bit. The third position is 2 to the power of 2. Remember, the first bit is 2 to the 0. And of course, 2 squared is 4. Just like before, this is a numeric calculation, so the REPL shows the decimal result. Wrapping the same call in bin shows the binary string equivalent. And as you can see, the third bit is on. Let's do the same thing with OR. A 1 bit in either value causes a 1 bit in the result. In this case, 4 1 bits. Well, that's and OR. How about not? Well, that's a bit unexpected. What happened here? For starters, Understand that just because you input 4 bits doesn't mean the math is being done on a 4-bit number. Python integers on most platforms are 8 bytes long. The number here isn't really 0110. It's 60 zeros, then 0110. When I used the tilde, all 64 of those bits were inverted. That gives you 61 1 bits, 2 zeros, and then a final 1 bit. This is the 2's complement representation of -7 decimal. The bin function then tries to be helpful. Rather than show the 2's complement number, it pulls the sign out front and then shows the positive value. What you're seeing here is minus, then binary 7. I believe I warned you about messing with bitwise math and signed integers. Hopefully, you're starting to see why. Let's do that again without the call to bin. Like I said, -7. Doing it another way might be weird, but it is consistent. You might recall from the lesson on 2's complement that not 0 is -1, and calling bin gives the sign magnitude output once again. Okay, so this is a bit ugly. Is there anything else that can be done? Well, sort of. Let me import the C unsigned int 8 object from the ctypes module. This module is typically used to interact with C language extensions. CUINT8 is short for C language unsigned integer 8 bits. I've renamed that to the slightly more friendly unsigned byte during the import. Creating an unsigned byte with a value of -42 gives 214 decimal. As the byte is unsigned, the 2's complement representation of -42 has flipped the same bits that result in 214 in unsigned mode. You can use the value accessor of the unsigned byte object to get the contents back out as a regular old integer. Great, so this solves our problem. Why did I spend all that time talking about the fact that Python doesn't have an unsigned integer? Why not just use the ctypes library? Well, turns out ctypes doesn't support bitwise operations. They're helpful for conversions, but can't be used as a replacement for an unsigned int. What's that old saying about skinning cats? Let's look at the array object from the array module. You can construct an array object using the small b template, meaning signed bytes. Or you can construct one with the capital B template, meaning unsigned. Using the 2bytes method on the signed value and importing that into the unsigned object with the fromBytes method, gives the familiar 214. This is another way of converting things back and forth. You can see the bits with the bin function, but unfortunately, if you start doing bitwise operations on these, it converts them to integers first. Not the same problem as ctypes, but it still doesn't solve the issue. There is yet a third way of converting byte values. The struct module is useful when dealing with packed binary data. Like the array object, it takes a template. Capital BB means 2 bytes, unsigned, like the array. This takes the signed -42 and gives you the unsigned binary representation. But also, like the array, if you start manipulating these values, you're back in integer land and all the problems that entails. There is a solution, but it doesn't come standard with the Python library. NumPy is a third party scientific calculation library. It is quite popular, and the underlying implementation is built in C, so it is also very performant. NumPy provides a number of alternate data types, including unsigned ones. To install NumPy, use pip, As always, it is best practice to do this in a virtual env. With NumPy installed, I can import the unsigned 32-bit integer. Like everything in Python, this is an object. Unlike the C types, NumPy's objects support bitwise operators. And remember good old -7? A solution. This isn't a negative number, and it also isn't the weird sign magnitude binary string. This is an actual inverted unsigned int. The REPL shows the integer value, but underneath, this is still a NumPy object. And looking at the type, you see it's a NumPy uint32. NumPy provides different byte sizes for its unsigned int. Here's the 8-bit one. And the ugly -7 problem has gone away. Depending on your use case, NumPy is probably overkill. If you're just keeping some binary flags and sticking with positive numbers, you don't need this. But if you're doing hardcore bit manipulation, having access to a true unsigned value could be useful. You've seen and, or, and not. Next up, let's get shifty with it. I apologize to Rick and Morty fans everywhere. In the previous lesson, I covered the bitwise operators and, or, and not. In this lesson, I'll show you how to use bitwise shifting. The left and right shift operators move the bits a number of positions to the left or right, respectively. New bits shifted in are of 0 value. Because each bit in a binary number is a power of 2, a bit shift is equivalent to a multiplication or division by 2. This is no different than multiplying by 10 in decimal. Shift the digits left and add a 0. Shifting is usually more performant than multiplication, and so this is an old school trick for times 2. This trick was very common in the gaming industry with low-level languages. It is an old school trick, though, and not really worth it anymore. Optimizing compilers know this trick and will do it for you, with the added benefit of not confusing the programmer who is maintaining your code. Let's start by shifting some decimal values. 4 shifted left by 1 is multiplying by 2, giving 8. 4 shifted left by 4 is multiplying by 2 4 times. That's 16, giving a result of 64. No different for non-powers of 4. Now, 312 is bigger than a single byte. What if you only want to deal with a single byte? Python doesn't have a byte data type, but you can emulate it with a bit mask. A bit mask is a series of bits that you typically AND with a number. Oftentimes, these masks are a series of ones. In this case, 255 is 8 ones in binary. Applying the mask to the bit shift removes any bits above the 8th position, mimicking an 8-bit byte. The bits above the 8th position are gone, and what is left from 312 is the lower 8 bits, giving 56 in decimal. Shifting right is division by 2, and for numbers that don't evenly divide, it works like a floor division. Python's double-slash division operator is a floor division, which contrasts to the regular division operator, which in this case results in a float. How about some negatives? Shifting isn't as problematic as knotting. 2's complement is happy to multiply by 2. No different for right shifts either. You may recall that I said that the bits shifted in are zeros. That's a bit of a lie, oversimplification. Python actually does what is called an arithmetic shift. That is a shift that preserves the sign bit. Think back to those negative numbers I just shifted for you. It felt all reasonable that -16 shifted right by 1 is -8 because of the whole division by 2 thing. But if a 0 had been shifted in on the left side, like with positive numbers, you wouldn't get -8. You'd get a positive number because you're pushing the sign bit out of the sign position. This is called an arithmetic shift. By contrast, the other kind of shift is called a logical shift. A logical shift ignores the sign bit and pushes a zero in, changing negative numbers. Some programming languages support a logical shift operator. In Java and JavaScript, it's three greater thans. Other languages automatically choose between arithmetic and logical operators based on the data type the operation is being invoked upon. Python doesn't support anything but arithmetic, but you could mimic the logical shift with the judicious use of a bit mask. Okay, so you've now seen the common bitwise operations in Python. What good are they? In the next lesson, I'll run you through some common use cases for bitwise operators. In the previous lesson, I showed you bit shifting in Python. In this lesson, I'll give you several examples of where bitwise operations get used in practice. A common use of bitwise operators is to manipulate a bit flag. A bit flag is just a binary value where each bit represents something that is either on or off in your software. These were extremely common when memory was more expensive, but less so now. I don't know it for a fact, but I'd be very surprised if each of the dots in the original Pac-Man game wasn't a bit in a binary flag. As Pac-Man consumed a dot, the bit in the flag would get toggled. A more memory-intensive mechanism would be a list or array of booleans in Python. There are situations, though, where a binary flag is easier to read and interact with than such a list. Consider the following code in the top window. The box object describes a box you might draw to the screen, having between 0 and 4 sides. I actually wrote something similar in the open source library Schematics recently for a widget that draws rectangular borders. Within the class, there are 5 constants. The first is used to indicate that the top of the box should be drawn. The second is the bottom. I've written it here as 1 bit shifted a single position to underscore the fact that this is a bit flag. You're just as likely to write the decimal number 2 in the real world. The third and fourth flags are for the left and right sides, each subsequent value being a bigger bit shift. The fifth constant is a bit mask used to determine if either the left or right sides are on. It's built using the left and right constants combined with a bitwise OR operation. The initializer on line 9 takes an integer. A more robust one would check that only valid bits are used or mask out the value, but I was lazy when I wrote this code. There are 2 methods of interest. The first, on lines 13 and 14, checks if any side is turned on. It does this by applying the bit mask called sides against the internal bit flag. If the box has either the left or right side turned on, the result of this AND operation will be a positive number. You could just return that, but for completeness' sake, I cast it to a Boolean value. The second method checks if both the left and right sides are on. This is a similar kind of calculation to the one before. The sides bit mask is supplied against the internal bit flag, but this time, rather than just checking truthiness, it is compared against the mask itself. If both left and right are on, then the result of the AND will be equivalent to the mask. This time I didn't bother with the cast to Boolean. Let's play with this in the REPL. First, I'll import a box. Now I'll create a box specifying the top and right sides. And because the right side is there, has side is evaluated as true. But has both sides is false. Let me construct another box. This time with everything but the bottom side. Has side is true. And has both sides is true. Although you could achieve the same thing with 4 booleans, checking if one or both sides is on would mean multiple if-else clauses. Sometimes a binary flag is not only more compact, but also easier to read. With the correct application of bitwise operations, you can arbitrarily turn on or off any bit in a bit flag. Let's look at another example to see this in practice. Like the box example, this door object stores an internal flag. This one is called door state. The initializer sets the starting value to 0, which will mean all the doors are closed. The open door method opens the door in the given position. Opening a door means setting the corresponding bit in the flag. To set a specific bit, first you create a mask by shifting 1 by the specified position. Then OR equals the mask with the flag. All the Bitwise operators support an op equals variant, meaning you don't have to write self.doorstate equals self.doorstate or mask. It saves a bit of typing. To close the door, you do something similar. First, create a mask for the bit representing the door's position. Then, invert it. The resulting mask will have ones for everything but the door you're closing. And equals this mask, and the door in question will be set to 0. You can open and close a door. How about querying the door's state? I've implemented 2 different ways of accomplishing the same thing. Lines 12 and 13 are the first version. Once again, construct a position bit mask. With the mask, simply AND it with the flag. The result will be greater than 1 if the position in question is set to open. As all numbers but 0 are truthful, this can be used like a boolean. The second variation on the same thing is in isOpen2. This time, instead of creating a position mask, I shift the flag value by position. Remember, this doesn't actually change the flag. It returns a new value that is the shifted version of the original. This will cause the least significant bit of the result to be the bit representing the door in question. The last step is to use a mask of 1 to determine the truthiness of that least significant bit. Both methods isOpen and isOpen2 accomplish the same thing. The one advantage of isOpen2 is that it always returns either 0 or 1, whereas isOpen returns 0 or some positive number. Depending on your use case, that 0 or 1 thing could be useful. The final method of the doors object toggles the door in a given position. If it is open, it gets closed. If it is closed, it gets opened. This might seem strange in real life, but in a game where there is only one button to change the state of the door, toggling would be exactly what you'd want. To toggle a bit, you use the XOR operator. Like with the other methods, create the position bit mask, but this time XOR equal the value. Remember that if both bits are on, XOR results in 0. If the door is closed, the XOR results in 1, meaning open. If the door is open, 1 XOR 1 is 0, closing the door. Let's play with this object in the REPL. First, I'll import it in. Then I create a hallway. Now I'm going to open door number 3. Monty Hall, eat your heart out. Looking at the door state, you see that the 2 to the third bit is set, giving 8. Looking at the binary equivalent, you see the 4th position on. Evidently, our hallways are 0 indexed. Now, I'll open another door. Here's the decimal and the binary state of the doors. Testing is open. Any value greater than 0 means the door is open. Doing it again with a closed door gives the appropriate result. Let me try this with the isOpen2 variant. Notice the result is still true, but the value is different. And that's a closed door. Finally, let's toggle something. The 4th bit got turned off, leaving just the 6th on. Toggling it again puts it back in the 40 state. Another use of bitwise operations is when dealing with colors. Colors are commonly stored in RGB format. This is typically specified in hexadecimal. Remember that each digit in hex corresponds to 4 bits of binary. The RGB format is short for red, green, blue, with an RGB value having a byte for each color. There's often a fourth byte for transparency or alpha channel, but I'll be ignoring that for simplicity's sake. Consider the hex value 7F8053. This corresponds to 7F of red, that's half intensity, 80 of green, 1 bit over half intensity, and 53 hex of blue, about a third of full intensity. Those three colors combined turn into that drab olive. Don't blame me, blame Da Vinci. I'm going to do the same thing that I just did in that color swab. Here's the decimal equivalent. You can peel the red out of the color by shifting out the green and blue bytes. That's 2 bytes or 16 bits. And red is 127 of possible 255, making it half intensity. Showing the red in hex shows you that the 2 red digits have been extracted. To do the same for blue, you want to first isolate the blue portion using a mask, and then you can bit shift the result. There's the decimal, and the hex value showing you the correct blue digits. Now for the green. Green is already the least significant thing, so no shifting needed this time. Just mask out the other values. Here's the decimal and the hex. By using these operations, you can isolate the colors that make up the full RGB value. You could use other bitwise operations or even additions and subtractions to change the intensities of these values. Turning up the red by 10% would be a simple multiplication on the red portion. Once you've made the changes to a part of the color, all you need to do to combine it is shift things back together. Here, the value Lisa is ORed values of red shifted by 2 bytes, blue shifted by 1 byte, and green. As I didn't change any of the values, Lisa and Mona should be the same. And as they say in the country that probably shouldn't own this Italian painting, voila. The next lesson is optional. It does a deeper dive into using the same techniques that you saw in this lesson. The lesson after that, if you decide to skip this one, is on Big and Little Endian byte order. In the previous lesson, I showed you some examples of bitwise operators in practice. In this lesson, I'm going to talk about the 2 different ways that bytes are strung together to make larger numbers. Before digging into endianness, let's take a look at ways of getting at binary information for different types of data. In a previous lesson, I showed you how to use a bit mask as well as the struct module. Well, masking only works for integers, so let's dig into struct some more. Let me import the math module so I can get at a rather famous float. Who doesn't want some pie? Well, I'm a cake man myself. Anyway, as I mentioned, masking only works with integers. In case you were curious, floats aren't integers. So what if you want to see the bits that make up a float? The struct module is your friend. Let me start by importing the pack function. Then I'm going to use a template. The greater than D string here indicates how the value is to be packed into bytes. The messy result is due to how Python shows raw binary data. If a byte is within ASCII range, it shows it as the equivalent of an ASCII character. That first character is the @ symbol because the first byte grabbed from pi turns into the number 64, which is ASCII for @. Some of the other characters here are also printable ASCII, and some of them are hex escape sequences. Putting the packed bytes into a list makes it a bit easier to see the raw values. As promised, the first element was 64. Same data, just a different format for printing it out. What if you want to see the bits? Then you need to loop over each part of that list and change it into bits. I'm going to use a list comprehension with an 8-bit F string format to do just that. This loops over every byte inside of the list and prints it out using the F string. The result is the floating point approximation of pi in binary. Well, technically it's a string with the binary digits inside of it, but you get my meaning. Pack goes forward, you might guess that unpack goes the other direction. Just copy and paste that bit string into a variable and then unpack it. Same template as before. Unpack is expecting a series of bytes. The bytes function provides this. I'm passing in a comprehension that converts 8 bits of that bit string at a time into an integer, essentially reconstructing the output of pack from just a moment ago. And the end result is a tuple with pi inside. Why a tuple? Well, unpack can return multiple chunks depending on the template. I'll do the same thing, but with a different template to demonstrate this. And this time you get a tuple with 4 bytes inside. It is the equivalent of the same binary data as before, but this time it isn't in the float format, so you just see the pieces. That first number contains the float's sign bit, the 11 exponent bits, and 4 bits of the mantissa. The remaining 3 numbers are 16 bits each of the remainder of the mantissa, for a total of 64 bits in a double precision float. Each of the pack and unpack templates that I've used so far has had a greater than symbol in it. That symbol has to do with byte order, also known as endianness. That's what I'll talk about next. When dealing with values comprised of multiple bytes, the order of the bytes in the value is a convention. It can either be left to right or right to left. Big endian is left to right, meaning the most significant byte is at the lowest address in memory. This format is common in mainframes and some of the Power and ARM family of processors. On the other hand, little endian is the opposite. It's right to left. The least significant byte is at the lowest address in memory. The x86 architecture family is little endian. An example might shine some light on the differences between these two. The Python language isn't named after a snake, but after Monty Python, the comedy troupe. Monty Python's first show aired in 1969. Seems like as good a value as any to show off endianness. I've broken 1969 into a 4-byte integer here. Each of these 4 bytes would have to be stored in memory. Assume that the starting value to store these bytes is at memory address 5000, with each address spot being 1 byte in width. The big endian case puts the bytes in Western reading order. The first address has the leftmost byte. By contrast, little endian stores the least significant byte in the lowest address, acting like a stack. This is the same 4 bytes of content, but stored in 2 different fashions. The terms Big and Little Endian are a reference to the book Gulliver's Travels, where Gulliver meets 2 warring factions whose primary argument was over which end of a boiled egg to crack first, the big end or the little end. Depending on who you ask, this was biting satire about religious wars or a child's book filled with nonsense. So, why would you prefer one of these over the other? Well, neither of them really has an advantage. Little endian allows you to treat different sized values the same way. 1, 2, 4, and 8 byte values all get pulled out of memory the same way, popping the byte stack one at a time. This makes certain kinds of math operations a tiny bit more efficient in the CPU. Big endian, on the other hand, has the advantage of knowing the sign of a number easily. The most significant byte is always the first one, and of course, the most significant bit in that gives you easy access to the sign bit of a number. This difference isn't a big deal when you're dealing with a modern high level language. It's all abstracted away. In the early days of the internet, it was decided that byte order on networks was big endian. I suspect this is because most of the networking stuff was done in the early days at universities, most of which had mainframes, which were big endian. Some processors are actually configurable. These are called bi-endian, and a setting changes their mode. Some of the newer ARM processors that are common in mobile phones are bi-endian. Let's crack open the REPL and take a look at endianness. The byte order value inside of the sys module will tell you what endianness you have. I'm recording this on an Intel based Mac, so little endian it is. The 2 bytes method on an integer object turns the value into its raw byte representation. When doing so, you specify how many bytes you want and in which endianness. Remember that big endianness means the most significant bytes are up top. Our number is mostly zeros for the first few bytes, so the raw string starts with zeros. You can reconstruct the int from those raw bytes, getting 1969 back. And this is why you have to be careful with endianness. If you assume the wrong one and reconstruct, you'll get the wrong value. Building from the raw bytes with little endian order gives you something that is definitely not 1969 when it was sent 2 bytes using big endian order. The socket module is used for doing network stuff. Within the module are 4 methods for switching values back and forth between endian orders. This is host to network short. It converts the host's format, whatever that is, to the network's format for a short int. This is host to network long. Same thing, but converting to a long int. And of course, you can go the other way. This is network to host short and network to host long. If you're using Python to interact directly with the network, the socket library has your endianness needs covered. One final warning on endianness. Some file formats have specific byte orders. If you're reading raw data from a Windows bitmap file, you'll be using little endian bytes, no matter your platform. JPEG is even trickier as it supports both. Tired yet? Next up, the penultimate lesson: overloading bitwise operators for fun and profit. Hmm, sorry, my producer's telling me that profit thing is optional. Guess just have to stick with the fun part then. In the previous lesson, I showed you how byte orders are related to boiled eggs. In this lesson, I'll show you how to use the special methods inside of Python objects to overload bitwise operators. Everything in Python is an object. All the interactions between objects that look like operations, adding, subtracting, comparisons, etc., are actually mappings to special methods on those objects. These special methods all start with double underscores, sometimes referred to as dunder. For bitwise operators, the special methods are dunder and, dunder or, dunder XOR, and dunder invert. Let's go play with these in the REPL. In the top window here, I've created a new class called 4bit. In the spirit of the 4-bit adder in a previous lesson, I've created an object that stores only 4 bits. Note the little bit of trickiness in the declaration of the class. I'm overloading the int class. I'm doing that so that I don't have to write as many overloads. For example, all the comparison operations can be handled by the parent class. The int class uses a variable called num to store the value, so the initializer starting on line 3 does the same thing. I've added a quick check in the initializer to make sure nobody tries to create a 4-bit object with a value that is bigger than what can be stored in 4 bits. Let me start out by importing this into the REPL, and I'll create a 4-bit object. Because I've overloaded the special method dunderRepr on line 13, the REPL prints out this object in a friendly format. Any integer can be passed into 4-bit. Let me just scroll down on the code. The first special method I want to talk about is dunderAdd. This is what is called when two 4-bit objects are added together. The other argument is the object being added to this one. Line 18 adds our num value to the other object's num value, then masks it to make sure it stays as 4 bits. Let me just call it. And there you go. 7 plus 2 is 9. I've implemented other math operations as well, and you can look at those more closely in the sample code download if you like. Let's move on to the bitwise operators. Line 36 overloads the AND special method. Like add, it takes an other object. A new 4-bit is constructed with the values of the two objects ANDed together. Testing it in the REPL. Similar thing for dunder OR. How about XOR? And finally, the invert or NOT operation. In the case of NOT, I'm masking it. I don't want those pesky higher value bits getting in the way. Given our history with the NOT operation and negative values, this one deserves a bit more testing. And all those bits flipped to 0. Nice. For a little homework, you could take the code from the 4-bit adder from the skippable section and re-implement the dunderAdd method to use your digital circuit simulator. The overloading I've done is to make an actual numeric object do bitwise things, but you're not limited to that. Lots of objects overload bitwise operations to mean different things. For example, the set and frozen set objects overload OR and AND to mean set union and intersection, respectively. Python 3.9 added similar use cases to the dictionary object. Well, now, it's been a long journey. I feel much closer to you than when this all got started. Last up, I summarize all this stuff. In the previous lesson, I demonstrated operator overloading and how to write your own implementations of the bitwise operators. In this lesson, the final lesson, I'll summarize the course. Binary is the heart of all CPUs, and lately, CPUs are at the heart of everything. When I was a kid, a thermostat was two pieces of metal glued together on a stick. Now they have artificial intelligence and tend to run Russian botnets. Where was I? Right. Binary values are formed based on the concepts of base 2 numbers, where each digit represents a power of 2. Bitwise operators combine or modify one or more binary values. AND, OR, and XOR combine two values, matching the ones, selecting the ones, or exclusively selecting the ones. NOT operates on a single value, inverting all the bits. You can also shift binary values left or right. Python only supports the arithmetic shift, which is conscious of the sign bit, but other languages support logical shifts as well, ignoring the sign bit. Everything in your computer is a binary value, just mapped differently. Unsigned integers map directly to the powers of 2. Negative numbers need a different mapping, 2's complement being the most common. And floating point and fixed numbers are packed sets of bits, portions of each meaning different parts of the number they're expressing. Python is a little creaky when it comes to bitwise work because it doesn't have an unsigned integer type. This isn't a complete limitation, you can work around it, but you do have to be careful. Python stores integers in two different internal formats, fixed and arbitrary precision. The first usually uses 8 bytes and has a maximum value. The second has no maximum but isn't native to your CPU. As all the integers are signed, you need to be careful when dealing with bitwise operations, as it can create unexpected behaviors with negative numbers. Most times, when you're interested in binary, you're not going to be dealing with negative numbers, just the raw bits. Using a bit mask can help you enforce the use of a subset of bytes of your Python integer, getting around the negative number problem most of the time. You can use bitwise operations to implement sets of binary flags, get, set, and toggle individual bits in a value, and access portions of a value, such as the R, G, and B parts of a color. When bytes come together to make bigger numbers, the order they go in is different on different computer architectures. Big endian puts the bytes in left to right order, whereas little endian does right to left, like a stack of bytes. Some processors are capable of working in either mode. These are called bi-endian. Finally, the last topic in the course was on overloading the bitwise operators in Python. Special methods called dunder for the win. Please join me in thanking multiple people at OpenClipArt, Wikimedia Commons, and Stack Exchange for providing public domain and free-to-use diagrams. I'm grateful for their work, and so should you be. Without them, you'd be looking at scans of crayon drawings. Artistic, I am not. It's been a long journey. I'm glad you stuck with me through it all. I hope you found the course useful. Thanks for your attention.